Welcome, chemistry students. You are welcome to the second semester chemistry course, General and Inorganic Chemistry. Unit 3 of this course is on the covalent bond, and the present chapter, chapter 3.3, is on understanding molecular geometries, the VSEPR theory. VSEPR stands for valence shell electron pair repulsion theory. The present chapter is concerned with understanding molecular geometries or predicting molecular geometries based on the postulates of the valence shell electron pair repulsion theory. Now, so far in unit 3, that is the covalent bond, we have learnt about drawing Lewis structures, calculating the formal charge, valence bond theory, concept of hybridization. Now we move further and learn about the VSEPR theory. The instructor for this chapter is Dr. P. Sharada, selection grade lecturer in chemistry, St. Joseph's College for Women, Autonomous, Visakhapatnam. Learning outcomes. By the end of this chapter, the learner would be able to comprehend the scope of VSEPR theory, understand the order of electron repulsions, predict molecular geometries based on repulsive interactions in the valence shell of the central atom, and also realize VSEPR theory limitations. So, the purpose or the expected outcomes from this chapter are: you will know the scope of VSEPR theory, you will also understand the order of repulsions between lone pair bond pair and bond pair. You will also be able to predict molecular geometries based on the repulsive interactions between electron pairs in the valence shell of the central atom, and finally you will also be able to realize the limitations of VSEPR theory. Understanding molecular geometries, the VSEPR theory. The contents of this chapter are drawbacks of octet theory and theory of hybridization, introduction to VSEPR theory, steps to predict molecular geometries, some indicative examples, and finally limitations of VSEPR theory. Let us quickly recapitulate what we have learnt so far. In this chapter on the covalent bond, we have learnt about covalent bonding. Basically, covalent bonding involves the sharing of electron pairs, one or more electron pairs between the bonded atoms. And the purpose of covalent bonding is to attain stability. Then we have also learnt to draw the Lewis dot structures. See, electron pairs are shared between atoms, but if you want to show how the electrons are distributed in the valence shells of all the atoms that are there in the molecule, we make use of the Lewis structure. So, the Lewis dot structures are used to depict electron distribution in molecules. They focus only on the electron distribution in the valence shell of the bonded atoms. Here some examples are also shown about the Lewis dot structures. Of course, we have also learnt about the concept of hybridization, which is basically mixing of atomic orbitals of almost same energy to form equal number of identical orbitals with definite orientations. When the hybrid orbitals are oriented at a particular angle in a particular direction, then automatically the molecule also will have a similar geometry, a particular geometry which is matching with the orientation of the hybrid orbitals of the central atom. So, in this chapter, so far we have learnt about covalent bonding, which is about sharing of electron pairs. You can see here how electron pairs are shared, and both the atoms A and B have acquired the octet. You can see here the Lewis dot structures. SO2, sulfur is having one lone pair, oxygen is having two lone pairs, this oxygen is having two lone pairs, and sulfur and oxygen are having two bond pairs each between them. You can see the water molecule. So we have here we have shown how the electrons are distributed in the valence shells of the atoms that are bound by a covalent bond, that are bound through covalent bonding. It need not be a single bond, but that are bound through covalent bonding. You can also see the hybridization depicted here. There is one s orbital, there is one p orbital. So this is sp hybridization, and because two orbitals are participating in hybridization, you got two hybrid orbitals, and the two hybrid orbitals overlap with the p orbitals of the two chlorine atoms, so as to form the beryllium chloride linear molecule. So through hybridization we have learnt how to predict sp hybridization of the central atom leads to linear geometry. sp2 hybridization, plane trigonal geometry. sp3 tetrahedral. So more or less, by knowing about the hybridization of the central atom, we have learned to predict molecular geometries and also the bond angles. Now we move further and see, in some ways these theories that we have learned so far are unable to explain certain properties or certain structural features that we find later in this particular chapter. Lewis structures fail to explain bonding and shapes of molecules. What is the main drawback of Lewis structures? They only focus on the satisfying the octet rule and distributing all the valence electrons. They focus only on that, but Lewis structures will not tell us anything about the nature of bonding as well as the shapes of molecules. You can only say, you can only say two pairs of electrons are shared, or one pair is shared, two lone pairs, one bond pair. Only that much information is available, but direction of bonding or shapes of molecules is not explained by the Lewis structures. Octet theory. Of course, the Lewis structures are written based on the guiding principle of octet number of electrons, but this theory also could not explain shapes and stabilities of molecules. Octet theory does not explain the shapes of molecules. Of course, to a certain extent, if the valence shell is having an octet of electrons or an octet configuration, it is stable, but there are several examples where the molecules are stable, but the central atom does not have an octet of electrons. There are some examples where the number of electrons are less than octet. There are certain other examples where the number of electrons is greater than an octet. Now, what about hybridization? Hybridization to a large extent could account for many of the structural features as well as the reactions as well as the chemical and physical properties, but deviation in bond angles could not be explained by the concept of hybridization. For example, in ammonia, nitrogen undergoes sp3 hybridization, but the bond angle is not 109.5 degrees, it is only 107 degrees. Why? Hybridization is saying nitrogen is undergoing sp3 hybridization, so tetrahedral bond angle has to be there, but the bond angle is less than tetrahedral bond angle. This fact could not be explained by the hybridization concept. So the VSEPR theory tries to bridge these small gaps, or it tries to address these limitations and account for the deviation in the bond angles that has been noticed in certain examples. For example, you can see here water undergoes sp3 hybridization. Supposed bond angle is 109.5. But what is the bond angle mentioned here? You can see supposed bond angle is 105 in water, but it is only 104. If you see the ammonia molecule, you can see the bond angle is only 107. If you see the SO2 molecule, it has to be sp2 hybridization 120, but the bond angle is less than 120. So, in order to account for these anomalies, the VSEPR theory has been proposed. VSEPR theory, which is valence shell electron pair repulsion theory, predicts molecular geometry based on the electron pair distribution in the valence shell of the central atom. See, name itself is indicating this theory is focused only on the valence shell. Point number one. valence shell of the central atom only, point number 2. Number 3 is it is pertaining only to electron pairs that are present in the valence shell. So, it is concerned with the repulsive interactions between electron pairs in the valence shell of the central atom. So, and because of repulsive interactions, when somebody is repelling someone else, automatically they try to maintain maximum distance. So, by arranging the electrons at maximum distance, you can see here there are two electron pairs here. A is bonded to two X atoms. So, there is one pair of electrons here, there is another pair of electrons here. So, these two pairs of electrons keep maximum distance from one another at 180 degrees. Supposing there are three pairs of electrons in the valence shell of A, the three pairs arrange at a distance of 120 degrees from one another. But if you see here, this particular A is also bonded to two X and two bond pairs, but because this A is having two lone pairs also, now there is a bent, the bond angle is bent, that is it is less than 180 degrees. You can see here there is a bending, or there is a reduction in the bond angle because of repulsions between the lone pairs and also the lone pair and the bond pair. So, the valence shell electron pair repulsion theory is basically focused on explaining molecular geometries and deviations in bond angles based on the repulsive interactions between electron pairs in the valence shell of the central atom. Now, let us see here some examples are shown. So, this original concept was proposed by Sidgwick and Powell in 1940. They tried to explain molecular shapes based on repulsive interactions. Of course, the Sidgwick-Powell theory was further developed by Nyholm and Gillespie in 1957. They gave the present form of the theory, and VSEPR theory predicts molecular geometry based on electron pair distribution and their repulsive interactions. You can see here electron pair distribution in the valence shell of the central atom. Central atom valence shell is considered as a sphere. The valence shell of the central atom is considered as a sphere, and in this sphere electron pairs are considered to be localized as electron domains. So, molecular geometry will pertain to how many pairs of electrons or how many electron domains are there and how they are distributed in this particular sphere, which is the valence shell of the central atom. Now, shape of molecules depends on number of electron pairs, which includes both lone pair and bond pair as well as their distribution in the valence shell. Electron pairs in the valence shell arrange to minimize. When there is attraction, they try to come together. Positive charge, negative charge, they have attraction, so they try to come closer. That's what we have learnt in the ionic bond. But when there are repulsive interactions between electron pairs in the valence shell, they try to get farther apart. Why they try to get farther apart? So as to minimize repulsion. Now you can see here multiple bonds. One of the salient feature of this theory is that multiple bonds are treated as a single bond with super electron pair. Suppose there is a double bond. That means there are two pairs of electrons, but still it is considered the two pairs of electrons. That means 4 electrons are considered as a super electron pair. So, this particular theory treats multiple bonds also as a single bond and the electron pair as a super electron pair. You can see here in the molecular geometries that are projected, if A is surrounded by two pairs of electrons, two bonding pairs of electrons, they arrange at 180 degrees. If A is surrounded by three bonding pairs of electrons, they arrange at a distance of 120 degrees. If there are 4 bonding pairs of electrons around A, they distribute at 109 degrees 5 minutes distance from one another. If it is, you can see here, if there are 5 pairs, then they are arranged at an angle. There are 2 now, axial bonds and equatorial bonds. Equatorial bonds are in the plane, axial bonds are above and below. So axial bonds are at an angle of 180 degrees, one axial to another axial, but axial to equatorial is 90 degrees, and within the equatorial it is only 120 degrees. If it is an octahedral, that is if there are 6 pairs of electrons around A, then the bond angle is 90 degrees. Molecular geometry is an octahedron. This is linear, this is plane trigonal, this is tetrahedral, this is trigonal bipyramidal, and this is an octahedron. Applicable to all the resonance structures. Just as we said, Lewis structures can be drawn for all the canonical forms or all the resonance structures. You get resonance structures from Lewis structures only actually. So this theory is applicable to all the resonance structures that are possible. Now let us see the postulates already we have learned. Just quickly let us see for polyatomic molecules, that is if there are only 2 atoms, it's a diatomic molecule, then there is no doubt it is going to be a linear molecule only. But for polyatomic molecules with greater than 3 atoms, number of electron pairs, that is lone pair plus bond pair in the valence shell of the central atom determine molecular geometry. Electron pairs minimize repulsion by maximizing distance between themselves. Then the order of repulsion. Now let us see the order of repulsion. Lone pair repulsion is greater than lone pair bond pair repulsion, which is greater than bond pair repulsion. So what is the order of repulsions? Lone pair greater than lone pair bond pair, which is greater than bond pair repulsion. You can see in this picture that is projected, see lone pair is like a big hat, you know, ammonia molecule is shown here. Above nitrogen, on top of nitrogen, there is one lone pair. See, lone pair is occupying so much space, you know, because lone pair of electrons are under the influence of one single nucleus. They occupy a large volume. They occupy a lot of space. You can see the blue region is the region occupied by lone pair itself. The remaining, you know, there are 3 bond pairs. So the 3 bond pairs are pressed closer, and that is why there is a reduction in bond angle. Nitrogen is here, the 3 hydrogens are here. These are the 3 bond pairs. Bond pairs are pressed closer. This is the zone, you know, bond pair zone. And bond pair zone, 3 bond pairs are occupying so much less space, whereas one single lone pair is occupying so much space. So lone pair repulsion is greatest. This is followed by lone pair bond pair repulsion. You know, this is lone pair, this is bond pair, lone pair bond pair repulsion, and minimum repulsion is between bond pair. Why? Because bond pairs are under the attractive influence of 2 nuclei. Repulsion will be minimum between the bonding pairs of electrons. Bond pair repulsions are minimal. Then presence of only bonding pairs will impart regular geometry, symmetrical geometry, regular shape. If the central atom is having only bond pairs, it will give a regular shape or a symmetrical geometry to the particular molecule. Then presence of lone pairs, we have been learning, you know, hybridization could not explain. sp3 hybridization is there in oxygen of water, but bond angle is only 104, it has to be 109. Why is the deviation? Hybridization concept could not explain. Now we are getting the answer. If there are only bonding pairs on the central atom, no deviation in bond angles. Perfect bond angles you will get. Tetrahedral bond angle 109 degrees. That is why CH4 carbon is the central atom, no lone pairs, so 109.5 degrees bond angle is maintained. But if there are lone pairs on the central atom, there will be deviation in bond angle due to distortion in molecular geometry. Molecular geometry is distorted and there will be some deviation from the expected bond angle in the particular molecule. Now let us see order of electron pair repulsions. This already I explained. See, lone pair repulsion greater than lone pair bond pair, which is greater than bond pair. This is ammonia, only one lone pair. So 3 bond pairs are pressed closer. You can see red lines are bond pairs. The violet ball or the purple colored ball is the lone pair. Lone pair is occupying a lot of space. So bond pairs are pressed closer, less than 109 degrees. Bond angle is only 107. You can see here water. Oxygen is the central atom. Oxygen is having 2 lone pairs here. 2 lone pairs repel one another. Lone pair will repel bond pair also. That means there are 2 repulsions. Lone pair, bond pair. The minimal repulsion is between bond pair. So bond pairs are pressed closer, even closer. So here it is due to one lone pair. Bond angle reduction is from 109 to 107. Here bond angle reduction is from 109 to 104. That is further reduction, and molecular geometry is only angular. Now let us see the steps to predict molecular geometry. All this we have seen. Linear, if there are 2 bond pairs. We are speaking only of bond pairs, no lone pairs. Only 2 bond pairs means molecule is linear, bond angle is 180. 3 bond pairs, then molecular is trigonal planar, 120 degrees. By lone pairs or bond pairs, we are referring only to the valence shell of the central atom. We are referring to the valence shell and the number of electron pairs in the valence shell of the central atom only. First we draw the Lewis structure. Already we have learnt how to draw Lewis structures. So draw the Lewis structure of the molecule or ion. Arrange electron pairs around central atom with maximum separation. So after drawing Lewis structures, central atom electron pairs have to be arranged with maximum separation and assign A, X, N, E, M. A is the central atom, X is the bonded atom, Xn will refer to the number of bonded atoms, Em will refer to the number of lone pairs of electrons. E will refer to lone pair. X will refer to bonded atom or the bonding pairs. Now you can see A is the central atom, N is the number of bonded atoms, which is X, and M is number of lone pairs of electrons in the valence shell. Then you identify molecular geometry based on lone pair, bond pair, and bond pair repulsive interactions, and then predict the bond angles. Here you can see when there are no lone pairs, geometries are regular. The molecule will have a regular geometry and bond angles are also perfect. You can notice the bond angles in the molecules. There is no deviation from the expected. So far in this video, we have learnt about the postulates of VSEPR theory and the applicability of the theory in respect of molecules where the central atom does not have any lone pairs of electrons, where the molecular geometry is regular and where the bond angles are just as predicted. In the following video, we will learn about molecular geometries where the central atom contains one or more lone pairs of electrons. We stop here. Thank you. All the images in this video are adapted from open source website on the internet. Thank you.